Hi, everyone. This is my summary of Unit 4. So I'm going to bring up, first of all, just the examples that I'm going to talk through. So Unit 4 is where we get introduced to game theory. And what we're going to do in this video is kind of talk through the two different types of games that you have encountered, simultaneous games and sequential games, and kind of use various examples to introduce or to kind of go over some key ideas, key concepts that we can use when thinking about how games will play out. So I'm going to start by looking at simultaneous games. And firstly, and most important thing, what do we mean by a simultaneous game? Well, it's where we assume that each player in the game, each person who has to make a decision, where those decisions happen at the same time, right? So I can't kind of wait and see what the other person's doing. We both have to make a decision at the exact same time. And a second kind of key idea that I'm going to refer to this term quite a lot is the idea of strategies. So in every game, players have strategies. And all that means is they have options. They have different things that they could do. Okay. So down here, looking at this payoff matrix, which I'll explain what that is in a second, a nil has two possible strategies. One is to grow rice, or you could say to play rice. And the second is to grow cassava or play cassava. Okay. And Bala, in fact, has the same two strategies, rice and cassava. So strategies just tell us the different options the players have. And then what this object here is, this payoff matrix does, is it shows us the payoff or the utility or the welfare that each player will get out of every possible set of choices, every possible set of strategies. So to give one example, if a nil chose to grow rice and Bala chose to grow rice, a nil would get a payoff of 1, Bala would get a payoff of 3. All right, so all we're doing here is showing the different payoffs from all the different possible sets of strategies. So to kind of figure out what players will do in a simultaneous game like this, I think it's a nice thing to do to start with is to think about the idea of best responses. Okay. And what we mean by a player best responding is where they think, right, if the other person in the game picks this strategy, what's the best thing I can do? What should I do that will give me my highest utility? And so what I'm going to do is kind of go through each possible scenario and sort of underline what the best response of each player would be. So I'm first going to think about things from a nil's perspective. So if I'm a nil and I think through, well, if Bala decided to play rice, to grow rice, what should I do? Well, if I grew rice, I would get a payoff of 1. But if I grew cassava, I'd get a payoff of 4, which is obviously better. So let me underline that. So the best response of a nil to Bala playing rice is to play cassava. Well, now let me think, well, what if Bala played cassava? She grew cassava. Well, if I go with rice, I get 2. I grow with cassava, I get 3. 3 is obviously bigger than 2. So underline that. That's the best response of a nil, playing cassava when Bala plays cassava. So now let's flip to the other perspective. Let's imagine that we're Bala. And so Bala's thinking, okay, if a nil plays rice, I can play rice and get 3, or play cassava and get 2. I'm going to choose to play rice because 3 is better than 2. Now, final one, if a nil plays cassava, Bala thinks rice will get me 4, cassava will get me 1. I'm going to choose to play rice. Okay, so what we get from this is we actually find in this particular case one outcome where both players are playing a best response to each other. And that's this one down here where I've underlined the 4 in both cases, right? So what we see here is if a nil is playing cassava, Bala wants to play rice, right? Doesn't want to change her mind, right? That's the best option for her, best response. But if Bala is playing rice, a nil wants to play cassava, does not want to change his mind. That's his best response. Whereas in all the other outcomes, the players wouldn't be happy. They wouldn't be best responding here. So the one outcome where they are both best responding, where they are both choosing the best possible action in response to the other one, is this one down here. And that is what defines what we mean by a Nash equilibrium. So when both players are best responding to the other person's choice, we have a Nash equilibrium. And this is a kind of a useful, like, what we call a solution concept for a game, because what this kind of indicates to us is if these players played this game and they kind of thought through all of their options, like rationally, they'd kind of realize that a really sensible thing to do would be for them to play these strategies, right? For Anil to play cassava, Bala to play rice, because in that case, neither of them would want to change their mind. Neither of them would want to do something else. So that's what we mean by a Nash equilibrium. And another kind of concept we can use to think about what players would do is the idea of a dominant strategy. What we mean by a dominant strategy is a choice, a strategy where the player wants to do that thing regardless of what the other person does, right? So let's say, for example, Anil wants to choose one of these options. Doesn't matter what Bala is going to do, he always wants to choose the same option. And here, that is actually the case. So if we actually think about things from Anil's perspective, if Bala plays rice, we saw that he would go for cassava. If Bala plays cassava, Anil goes for cassava. So regardless of what Bala is doing, Anil always plays cassava. Anil has a dominant strategy here. He's always going to play cassava. And Bala also has a dominant strategy, because if Anil plays rice, she plays rice. If Anil plays cassava, she plays rice. So she's always playing rice regardless of what Anil is doing. And because they both have a dominant strategy here, Bala to play rice, Anil to play cassava, this Nash equilibrium is also a dominant strategy equilibrium. Now, one thing I want to make very, very, very clear is if I was going to define or explain what the equilibrium is here, I wouldn't say it's where Anil gets 4 and Bala gets 4, right? To explain what an equilibrium is, we need to say what actions the players are taking. So the equilibrium here would be Anil plays cassava, Bala plays rice, and then you could go on and say, and the payoffs that they each get are 4 and 4. But the equilibrium is what actions, what strategies are they choosing? So one final thing before I move on from this example is just this idea of information. So a game like this, in order to kind of analyze it the way that I have, we need to assume that the players have perfect information. And what we mean by that in a game is that each player knows what strategies the other player has, right? So Anil knows that Bala can only play rice or cassava. Bala knows that Anil can play only rice or cassava. So they each know what the other person's options are, their strategies are. And the second part of it is they each know not only what payoffs they would get from each set of outcomes, they also know what payoffs the other player would get from each set of outcomes. So we have to assume that they know all of that in order to analyze the game like this, right? If there was some imperfect information, if Anil or Bala didn't know that one of them had another strategy or didn't know the other one's payoffs, then we wouldn't be able to come up with a neat solution like this at all. So in order to get here, we need to assume they have perfect information. They know what each other's strategies are, and they know what payoffs they'll get on the basis of each of those strategies. Okay, so that's kind of like our first example, lots and lots of concepts in there. So is a very, very famous game, which is called The Prisoner's Dilemma. And one really key thing that we need to watch out for here is that in this case, the numbers represent an amount of time in prison. So actually, we're assuming the players don't want to go to prison. So actually here, smaller numbers are going to be better. So what I'm going to do is work through this using the idea of best responses. So I'm going to take Thelma's perspective first of all. And so if Louise plays the strategy deny, right, then Thelma has a choice between playing deny herself or accuse. And remember, we want lower numbers here. So Thelma has a choice between 1 year in prison or none. So she's going to go for none, right? Now, if Louise plays the strategy accuse, then Thelma can play deny and get 10 years in prison, or play accuse and get 5 years in prison. So 5 is less than 10, so we'll go with that. Now, from Louise's perspective, if Thelma was going to play deny, then the best thing for Louise to do would be to go with accuse, because 0 years in prison, better than 1. And if Thelma's going to play accuse, what's the best thing to possibly do? Well, deny would mean 10 years in prison. Accuse means 5 years in prison. So go with that. And what can we see that we found here? Well, we have one Nash equilibrium, right? And the Nash equilibrium is where both players spend 5 years in prison. And I believe this also happens to be a dominant strategy equilibrium. Now, why is that? Because let's just kind of go back and maybe think about things from Thelma's perspective. So Thelma, if Louise plays deny, Thelma goes with accuse. If Louise plays accuse, Thelma goes with accuse. So Thelma is playing the strategy accuse regardless of what Louise does. And I won't go through it, but it's the same thing for Louise. So they both have a dominant strategy here, which is to play accuse. And so this is a Nash equilibrium because both players are best responding to each other, but it's also a dominant strategy equilibrium because both players are choosing a strategy that's a dominant strategy. Now, why this game is a little bit strange is because if the players both played deny, they'd be better off, right? They'd both only get 1 year in prison as opposed to the 5. And the kind of key lesson we kind of take away from this game is, well, why are they not doing that? And it's because of the fact that they're worried about the other player sort of screwing them over, right? So if I'm Thelma and I think, okay, well, if I go with deny, then I'll only get 1 year in prison. But I'm slightly worried because if Louise knows that I'm going to play deny, she might go, well, play accuse because then she would get less. And then I'd end up with 10 years. So that kind of scares Thelma away from playing this deny strategy. And so if both players are being kind of completely selfish, then although it seems a bit strange, they will end up both just playing accuse because of that fear of the other player kind of screwing them over, the other player, well, I say screwing them over, the other player making what will be a rational response, what would be a best response to one of them playing deny. So it seems like a bit of a strange outcome, but that's this kind of what shows us like a bit of a strength of game theory is it can help explain what seem like sometimes counterintuitive outcomes. Okay, so that's the prisoner's dilemma. So let's now move on to, well, how sometimes taking things from a selfish perspective might actually lead us to sort of the wrong outcome. And quite often in game theory, and particularly if you get shown a payoff matrix and you're thinking about what players are going to do, you should operate on the basis that the players are going to behave selfishly, that all they care about is getting that best possible payoff they can for themselves. They don't care about the other player. But what this example shows us quite nicely is that if we kind of remove ourselves from this idea that the players are completely selfish, then the outcomes of a game could be different, right? So what this graph here does is it maps out the payoffs in all the 4 different scenarios. So for example, if Anil and Bala both play strategy I here, like this, I think this fertilizer IPC, they both get 3, right? Whereas if they both play the strategy Terminator, TT, they both get 2. And then we can see if there's like a mix, Anil will get 1. If he plays the strategy, let me check this. Sorry, Anil will get, Anil gets 1 if, actually, I think this shows Anil getting 1 if he plays the strategy no, this is right. If he plays the strategy IPC, and then Bala plays the strategy T, plays Terminator. And then our final one is just the reverse of that. So where we typically begin with game theory is to assume that the players are behaving completely selfishly. And these vertical blue lines on the diagram here show us indifference curves when Anil is completely selfish. Now, why do these vertical blue curves show that? So remember, indifference curves show us level of constant utility. So if we're at this point here where Anil gets a payoff of 2 and Bala gets a payoff of 0, Anil has this level of happiness. And then as we move up this line, Anil is still getting 2, right? Constantly getting 2. Bala is getting more, getting a higher payoff, but this has no impact on the utility of Anil, right? He's just as happy if he gets 2 and Bala gets 0 as if he gets 2 and Bala gets 5. Same level of happiness, doesn't care about her payoff. And the one at 4 shows us a similar thing, right? Further to the right, Anil has a higher level of utility. This is a higher indifference curve. But as Bala's payoff increases, has no impact, right? Doesn't change his level of utility. Whereas the curved ones here show us now Anil having some level of altruism, as in, by altruism, some level of happiness coming from seeing the other player, seeing Bala benefit. So how do these curves demonstrate that to us? Well, let's take this blue curve here, right? And we can see that on this particular blue curve, Anil has this level of happiness, this level of utility if Anil gets 3 and Bala gets 3. But if we move up in this direction, the level of utility Anil has is staying the same. But as we move in this direction, Anil's payoff is getting smaller, right? Smaller and smaller and smaller. Bala's is getting bigger. So Anil is just as happy to get a smaller payoff than 3 as long as Bala is getting a higher payoff than 3. So this shows us that Anil has an element of altruism in his preferences, because he doesn't mind losing some of the payoff as long as Bala gets more. And if we look at the kind of whole example now, what we see is if Anil is completely selfish, then the outcome that Anil would want is this one here, right? Where Anil plays T, and Bala plays I, and this would make Anil the happiest he could possibly be, right? The best possible outcome for him if he's completely selfish. But if we consider there being a possibility of altruism, then actually Anil would be happier over here, right? With this would be the best possible set of strategies where they both play I, they both choose IPC, and this would be better. So what this is designed to show us is if there is altruistic preferences, if there are altruistic preferences, then the outcome of the game could be different. But my very, very, very strong advice is if you're presented with a payoff matrix or later a game tree, always assume, unless told otherwise, that the players are going to behave selfishly. And on that basis, then use the things that we've talked about, like the best response idea to figure out what they'll do. And then this idea about altruism and some other things I'm going to talk about in a minute, these can be used as a nice evaluation for you to kind of point out, well, this is what the outcome would be if they're completely selfish, but if they're altruistic or if they have reciprocal preferences, then things might be different. But always start from the assumption that the players are behaving selfishly. Okay, so next thing I want to talk about before kind of going through all these things that could change the outcome is this idea of a public goods problem. So what we kind of see here is we are imagining that we are this person, Kim, and Kim has kind of got this like setup where there are, I think there's Kim and then there are like various other farmers. And these farmers are kind of deciding about whether they should contribute to, say, like an irrigation project. And so what this diagram is showing us is, so the blue shows us what Kim's payoff would be if she contributed. The red shows us what the payoff would be if she didn't contribute. So if none of the other farmers contribute, but Kim decides to, then she gets a payoff of -2. But if none of the other farmers contribute and Kim doesn't either, she gets a payoff of 0. So obviously 0 is better than -2. So in this case, where no one else contributes, the best thing for Kim to do is not contribute either. Now let's think about, well, what if one of the other farmers decides to contribute? So if that's the case, if Kim also contributes, she gets a payoff of 6. If she doesn't contribute, she gets a payoff of 8. So again, 8 bigger than 6. Her best response here is to not contribute. Then we go to 2 farmers contributing, and we're in the same scenario, right? If Kim does contribute, she gets 14. If she doesn't, she gets 16. 16 is better than 14. If she's being selfish, her rational response is not to contribute. And we're going to get the same thing here if we have 3 other farmers contributing. So regardless of what the other farmers do, Kim will, if she's being selfish, will have a dominant strategy here, right? If she has a choice between contributing and not contributing, the dominant strategy is to not contribute. But if we thought about this game from the perspective of the other farmers, it would be exactly the same, right? They would face the exact same choice. And so what's the outcome going to be here? Everybody's going to choose not to contribute, and no irrigation is going to happen, and then the payoff will end up being 0. And this is kind of how we can illustrate the idea of a public goods problem with a game, because what we kind of see with public goods is that, you know, nobody wants to provide them. Nobody wants to kind of pay the cost, because then everybody else will just benefit without having to contribute. And this game, this public goods game, shows us like the kind of reasoning behind why that might happen. So this seems a bit sad, but in reality, we know that public goods can be provided, I mean, sometimes with government intervention, but there are a few concepts that can help us understand why people might not, you know, why we might not get the outcomes that we've seen in lots of the previous games. So we saw already, altruism can be one. If I, as a player, gain some utility from seeing the other player benefit, that might change my choice, right? I then might act differently. Other things that can kind of change behavior in a game, this idea of reciprocity, right? What if there is some history of interactions between me and the other person in the game, and last time we interacted, that person was really kind to me, maybe I'll feel like I should be kind back to them. Or if I know we're going to encounter each other in the future, then again, maybe that will make me think, oh, I should try and be nice now because I might get some benefit later on. There's also just the idea of fairness, that like within a society, it might be the case that in certain circumstances, the norm, the like normal thing to do is to behave in a certain way. And maybe that way isn't kind of going to lead to you maximizing your payoff, but it's the fair thing to do, right? And so you kind of go along with that. But a last and really, really interesting way of kind of thinking about interactions and why we might not see the outcomes that we would expect is this idea that interactions are repeated, right? So if we took the prisoner's dilemma game or the public goods game, if we knew, and if the players knew that they were going to play this game again, they were going to repeat the interaction. And maybe if they were going to repeat the interaction several times, just the fact of repeating the interaction could change what they decide to do. In particular, because that introduces the possibility of players punishing each other, right? So if in the first round, one player did the really selfish thing and the other player didn't, the other player did the selfless thing, the altruistic thing maybe, then in the next round, the player who got kind of spurned might find a way of punishing the other one, right? They might sacrifice a bit themselves in order to punish the other player, because they're thinking in the long run, this might show them, if you choose the selfish option, I'm going to punish and it's going to be bad for both of us. And so then in the long run, you get better choices all around. So this idea of repeating interactions and being able to punish, that's kind of a key thing to then seeing different outcomes in games. Okay, so final kind of thing I think I wanted to talk about, in terms of simultaneous games, is the possibility of multiple Nash equilibria, right? So far, we've only seen games where there's only one Nash equilibrium, right? This setup here, so all that's happened now compared to when we looked at this game before, where they've got choices between rice and cassava, is now the payoffs have changed a little bit. So let's kind of go through this using the best response idea. So if I'm Anil and Bala chooses rice, if I go with rice, I get 0. If I go with cassava, I get 4. Obviously 4 is better. If Bala goes with cassava, I go with rice, I get 2. I go with cassava, I get 1. So I'm going to go with rice because 2 is better. Now let's flip things and think about things from Bala's perspective. So if I think Anil is going to choose rice, I choose rice, I would get 1. I choose cassava, I'd get 2. That's better. So go with that. If I think Anil is going to choose cassava, if I choose rice, I get 4. If I choose cassava, I get 0. So I'm going to go with rice because that's bigger. And what we see here is there are 2 sets of strategies where the players are best responding to each other. We have 2 Nash equilibria. Now, if we look at this for a second, it's pretty clear that one of the Nash equilibria is the other, right? Okay. Like short, where Bala plays this one's better. They both get a higher payoff than if they go with the other Nash equilibrium. And so in reality, like if this sort of game was played, we'd probably expect that the players would end up in this Nash equilibrium, this one that's better. But what this shows us is it's possible for the players to end up playing this, right? And if they did, they wouldn't want to change their minds, okay? Because they could end up with something worse if they did change their minds. So this other Nash equilibrium is a possible outcome of this game, less likely because it gives them worse payoffs. But you can imagine that, what if Anil had something in the back of his mind that, like, there was some family history of always wanting to grow rice that may give them like a stronger like preference for doing that, then maybe, and if Bala knew that, then maybe we would end up in this one, all right? But typically, if you see these 2 Nash equilibria, you'd expect the one with the higher total payoff to be the one that would occur, the one that would happen. So that is everything in terms of simultaneous games. Now let's talk about sequential games. So the big change here is that now it's no longer players making decisions at the same time. We have players making decisions one after the other. And so instead of a payoff matrix, what we typically do here is draw what's called a game tree, which shows us what players are going kind of when, like who's going first and what choice they have to make. And then as we move down the game tree, we then see other players going and what choices that they have to make. So this particular game tree, this represents, it's an example of what's called the ultimatum game. And so we have this person, the proposer, who has $100. And we see that in this particular version, they have 2 possible choices. One is where they could take this money, this $100, and offer the second person, the responder, an equal split, where the proposer gets 50, the responder gets 50. Or the other option is the proposer could say, I'll take 80, and you, responder, you get 20. And then after each of these possible choices, we then see the possible things the responder could do. So they could accept the 50-50 offer, and so then proposer gets 50, responder gets 50, or they could reject, and then each player gets nothing. And same thing after the 80-20 offer. The responder could accept, and proposer gets 80, responder gets 20, or the responder rejects and they both get nothing. So with this kind of game, with a sequential game, the way that we typically figure out what the equilibrium will be, what the kind of outcome will be, is we use this concept of backward induction. So we start with the final decision and think about what would the person making that final decision do. And then we go to the previous decision and think, well, based on that, what would the person making the decision before do? And the reason we do this is because, like, if I was the proposer and I'm thinking about which of these things to offer, well, to make that decision, I want to think about, well, what would the responder do after each of these, right? So that is why backward induction is like the kind of reasonable, the rational way to think about these problems. Because if you are involved in this game at any point, you always want to think about what's going to come next. So now we got to think about responder after each of these possible offers. So after the 50-50 offer, the responder accepts could get 50, rejects get 0. Obviously, 50 is better than 0. They're going to accept. Responder after the 80-20 offer. Well, they accept and they get 20. They reject and get 0. Again, they're going to accept. So regardless of which offer is made, the responder is going to accept, right? Because 20 is bigger than 0. 50 is bigger than 0. So the proposer knows this. The proposer knows that regardless of which offer he makes, the responder is just going to accept, right? So from the proposer's point of view, he's thinking, or she's thinking, well, which of these should I do? Well, if they offer 50-50, they'll get 50. If they offer 80-20, they'll get 80, right? That's obviously better, right? So this is the outcome the proposer wants to achieve. And this is going to be the kind of outcome of this game, right? This will be, maybe you could say, the equilibrium of this game. And again, be careful. The equilibrium, we need to say what the players are going to do. So what that means here is proposer's action is to offer an 80-20 split. Responder's action is to accept. And the outcome is that the proposer gets 80, the responder gets 20. So one thing, please be very, very careful about. If you wanted to, after having gone through this analysis, you could talk about, well, how the outcome might end up being different. Like something like, well, maybe the responder really cares about fairness. And, you know, if they didn't get the 50-50 offer, if they got the 80-20, they'd want to, you know, punish the other player. But based on the numbers we see here, they wouldn't do that, right? They wouldn't. Because when it gets to the point where they see this offer of 80-20, if what they're doing is comparing 0 and 20, we assume that they're trying to maximize their utility. Of course, they'll choose the 20. So a game like this, there's no sense of there being any sort of reciprocity or fairness in it at all. If we want to bring that into the game, we need to change the payoffs. And so the final thing I want to talk about is this same sort of game, except where now there is an element of reciprocity. And we can see that because now if one of the if the responder rejects, now we actually see they don't get 0, right? They get some other quantity, and that quantity that they get is going to depend on this value R, and that R is supposed to be a number, this reciprocity value. It measures the sort of strength of feeling that the responder has for fairness in this game, right? So bringing this in and seeing that we now have this as a possible payoff is going to change the equilibrium of this game. So we're going to approach this in the same way, right? Start with the responder. So the responder could accept and get some amount Y, or they reject, and the value they get from rejecting is R times 50 minus Y. So what we're going to do is think, well, what has to happen for them to accept? Now, why am I thinking about that? Because from the proposer's point of view, the proposer wants an acceptance, because X, whatever that ends up being, is going to be bigger than 0. So the proposer wants an acceptance. So now we need to think, what does the proposer have to do to get that acceptance? Well, they have to make it so that Y is greater than or equal to R times 50 minus Y. Now, I've done a little bit of a cheat here, which I did before when we saw these examples. I said greater than or equal to. So by doing that, I'm making the assumption that if the value of Y is the same as the value of R times 50 minus, that the responder will accept. All right. I didn't have to do that, but it just makes life a little bit easier to say when they're equal, acceptance will happen. So writing this down is going to be really useful, because now this is actually going to help us, from the proposer's point of view, figure out what offer they should make. So let's do like a quick little bit of algebra. So expand this out, we get 50R minus R times Y. bring this over to the other side, and we're going to get y plus ry has got to be greater than 50 times r. And then what I'm going to do is take the y out as a common factor and then divide by 1 plus r. So I get y has got to be greater than 50r over 1 plus r. So why is this really useful? Because what this tells the proposer is what value of y the proposer needs to offer in order to get the responder to accept. And this is great because from the proposer's point of view, what they want to do is make an offer that will be accepted, but make that offer as low as they possibly can, right? So from the proposer's perspective, if that proposer can now say, let's make y equal to this, and then the responder would accept, and then the proposer is going to get whatever x is, so say 100 minus this. And so this leads us to an equilibrium for this particular version of the game, where what the proposer does is to offer y, which is going to be equal to 50r over 1 plus r, and x, let's say if this is $100, would be 100 minus that. And in the responder would see that they are getting then a choice between sort of two equal things, right? The acceptance and the rejection would both give them this. And based on our sort of tie break, they would decide to accept. And then that's going to be our outcome. So proposer offers y equal to 50r over 1 plus r. And then for themselves, 100 minus that. And then the responder sees that and would accept. So the crucial thing, I'll really stress this again, is to kind of like we actively brought reciprocity into this game by bringing in this expression to show that when there was rejection, the responder gets some value from that. Okay, so if we want to bring reciprocity or altruism into the game, we have to bring it into the payoffs. If it's not there, right? If we have an example like the previous one, where we can see rejection just brings the responder nothing, then there's no sense of altruism or reciprocity or fairness in it. So always when you're analyzing a game, use what you've been given, analyze the situation that you've been given. And then, and most of the time that means you're thinking about players having just completely selfish preferences. And then maybe you could then talk about, well, if they did have altruistic preferences, or if they did have some sort of fairness norm, then the outcome could be different. But don't assume that the players have that unless you're explicitly told it, or like here, you're explicitly shown that they do have some reciprocity value. All right, I'll finish up there. I hope that was helpful. Yeah.